So we'll go ahead and get started. Just a few things just before we get started. First of all, it's a really exciting Barnard Year of Science. And I feel like every department just wants to show their best stuff and, help everybody in the whole world see why we love what we do. And chemistry is no exception. We're really proud of what we're doing in this Barnard Year of Science. So the event is both with people in the room and people on the webinar. And so at the end of Karen's talk, we'll field questions from everyone. We'll always open the floor first to students as I make eye contact with my student friends. But if you're on the webinar, you'll be typing your questions into the space provided for that in the webinar. And Laura and I will field questions from everybody, and questions in the room I'll repeat so webinar people can hear them. Okay, so that's to look forward to. And if you don't get all your questions answered, the material that Professor Goldberg is going to talk about today is really at the heart of a lot of our curriculum here in chemistry. So come see us another time, take more classes with us. I also wanted to just thank a few people. So my colleague, Dr. Jean Wadikin, is the Barnard Year of Science chemistry representative, and she's done a lot of things to make this month exciting. So thank you, Jean. Communication staff has been remarkable in helping us plan today. So thank you guys. Laura Hendrickson, our departmental administrator, has done a lot of work to make this day work, including lunches. So thank you, Laura. And then finally, I want to thank both our president and provost, who as our two top academic leaders at the institution have really been unwavering in their support for science. It makes Barnard a great place to do science, and it's really great to feel like you've got the support of those leaders. So Linda, thank you.
Thank you, Rachel. Thanks for setting the mic at exactly the right place for me. It's a rare thing. So hello, everybody. It's nice to see so many people in person, and welcome to the people who are on live cam, so to speak. So I want to thank everyone, first of all, for being here. Barnard is a very special place. As we know, we like to say it's singular for a whole set of reasons, among which are I'll just list a few bullet points if you bear with me. A focus on empowering young women to pursue their passions, to push boundaries, to ask questions, and to discover new insights. Academic excellence across the arts and the sciences. A world-class faculty that's tenured at both Barnard and Columbia, which is truly unique. A tight-knit and very special supportive community where our students return to no matter where they go and no matter what stage they're in their respective life paths. And access to New York City, and access, of course, to the university right across the street. So this is a special year, as Rachel said. This is called Barnard's STEM Year, or Barnard's Year of Sciences. It's an exciting time for the college. At the start of the semester, we launched this year with bold ambitions. Our goal is to tell the story of the power of women in STEM. Barnard has a history of excellence in the liberal arts, in the arts and humanities, which we have talked about quite a bit, but we haven't told the stories as widely, and we are not as widely known for our excellence in STEM, and our goal this year is to change that. More than ever before in our history, young women interested in the science are choosing Barnard. In the class of 2021, 34% of our students graduated with a degree in a STEM-related field, exceeding the national average, which is 26%, and that's pretty extraordinary. And furthermore, for the members of the class of 2021 who identified as underrepresented minorities, 36% majored in STEM-related or got STEM-related degrees which is significantly higher than the national average, which is 23%. We created several new programs and departments and pathways within departments. We know about computer science and neuroscience and behavior, both new to Barnard. They've grown tremendously in a very short time, and they're now among the top 10 majors. And we know about the SRI and the significance of the research opportunities we provide our students. It is truly unique. The program grew from formally about 40 students to over 242 students last summer. And that's Barnard supporting those students and PIs supporting those students, your faculty, in projects that allow you the opportunity to move forward and go forward at the highest level in your chosen careers. 10% of our outcomes are phenomenal. 10% of our students go on to medical schools. We track students who go on in the sciences, and we are the 9th largest producer per capita, given our size, of PhDs in the country, which is in sciences, which is really, truly incredible. So as you know, we're building a new building, and many of the faculty are involved and engaged in that process right now. It is a very exciting time for Barnard in that regard. We've raised over 85% of the funds that we need to build that building. And stay tuned, because we're moving fast, and there will be a lot of very interesting and informative things to share with you as time goes on. So let me now turn to introduce our speaker. First of all, we are thrilled to have Karen Goldberg with us today. As Professor Austin is very competitive, and she chose a really very impressive speaker for chemistry's part of the year in science. So as an undergraduate at Barnard, Dr. Goldberg pursued research projects with professors at Cornell, at Columbia, and at AT&T Laboratories. She then went on to the University of California at Berkeley, where she earned her PhD in chemistry. Following a postdoctoral year at Ohio State University, Dr. Goldberg joined the faculties at Illinois State University and at University of Washington before moving to the University of Pennsylvania as the Vagelos Professor of Energy Research. From 2007 to 2017, Dr. Goldberg served as director of the First National Science Foundation funded Phase 2 Center for Chemical and Innovation, the Center for Enabling New Technologies through Catalysis. In 2018, Dr. Goldberg was elected to the National Academies of Sciences, really the most significant and prestigious honor awarded to a scholar in the sciences. At UPenn, where Dr. Goldberg currently teaches and conducts research, the Goldberg Group focuses on the development of new catalytic systems to efficiently produce chemicals and fuels from a range of available feedstocks. Dr. Goldberg has already given much to the college. She is serving on the Board of Trustees, and she is serving on the Cultural Steering Committee, which is overseeing the building project. We are thrilled and proud of our association, our lifetime association with Dr. Goldberg, and we're thrilled and excited to welcome her here back to Barnard, her long-term home. Thank you.
Okay, should I turn this off? Okay, so thank you all. It's really exciting to be here. It's always a treat to come back to Barnard. And yeah, I kind of grew up here. So what I wanted to talk to you about today, as part of the Year of Science, right? It's great to come back and think about celebrating here in this year of science, where we're celebrating women in science from the past to the present to the future. And so by way of that, let's look back a little bit at the rich history that Barnard has of educating women in science. This I found on the website in the archives. This is actually a picture of what looks to be a chemistry lab. And I'm basing it by what's in the windows here, that this must have been Millbank. So this is where chemistry was in 1944. Then Auschwitz was built, you can see here in 69. This is actually a picture from 82, but those who are alums will notice that, you know, here's Lehman Hall still there. Doesn't look quite like that anymore. And then, but this is pretty much how it looked in 1982, 83 when I was here. And this is me graduating from Barnard in 1983. And the chemistry department looked very different then as well. So the chemistry department, these are the faculty who were here then. So some of the chem department alum will recognize these really great, impressive scientists and teachers. I owe so much to Bernice Siegel for her guidance and mentorship as I was a student here at Barnard. But you can see there's 4 faculty. There were actually 3 physical chemists and 1 organic chemist. But we move forward today. This is the campus today. And you know, you can see Auschwitz back here. This is the front of the Diana, this part of the Diana Center. That was Macintosh back then. And we see the beautiful new Milstein building. The chemistry department has changed a lot too. You can see now it's doubled in size, right? We have 8 tenure line faculty. So, you know, obviously we need to grow, and that's really the plans behind this future science building. So here's Auschwitz is going to be completely renovated, and then in addition is going to occupy the space between Auschwitz and Millbank here. So really it's going to be just a tremendous addition to science at Barnard, and I'm really excited to be part of that team. Okay, so let's get down to some science that obviously science is critical in our society. We've all seen that mostly we've seen that in spades in the last year, right? I mean, it's pretty incredible that we got to a vaccine for COVID inside of a year. Really excited that as part of the Barnard Year of Science, Dr. Corbet, who was head of the NIH vaccine research group, and now at Harvard, is coming to give a talk. So that'll be in the end of June. So another great addition there. But really, we've seen the effects then of the vaccine. You know, this plot is particularly compelling here. This shows when the vaccine rollout begins. And this is the deaths among nursing home residents. And you can see then this is all of US COVID deaths who were later to get vaccinated. You can also see plots like this, where we have the deaths that with the vaccine, and these are the predictions of where we would be without the vaccine, right? So clearly that's had a huge effect. But we have to remember that before COVID, our big problem was climate change. And guess what? It still is, right? So in climate change, you know, we've seen then that carbon dioxide levels going up, our temperature going up, our sea ice is melting. You know, this is from 2019 when everybody knew who Greta Thunberg was, right? And even then, the AMA says climate change is the greatest public health crisis, right? And we've seen it this past year, the past several years, in terms of more forest fires, droughts, tropical storms. All of this is coming into play. And we don't have a vaccine here, right? There's nothing we can go out and say that there's going to be one solution to this problem. It's a huge problem. And it's scary. But again, science is going to be the answer here. Okay, and we have as a society actually faced big problems like this in the past. So if we learn from history, this is a wonderful book here called The Alchemy of Air. And I would recommend this to both scientists and non-scientists because it's just beautifully written about the story of the Haber-Bosch process. And really what's happening then is that back in the late 1800s, I'm sorry, I'm trying to get this pointer to, seems to have lost the screen. Okay, so I'm gonna maybe not use the pointer so much. Okay, so the world population was increasing, and all the data. So you had plots, just like we see for climate change with CO2 rising. All the plots showed that there wasn't going to be enough, that there would not be enough food. And in 1898, Sir William Crookes gave his inaugural address as the president of the Royal Academy of Sciences in England. And he goes through all of this data and basically shows then that, you know, this is the statement he makes: England and all civilized nations, because it was mostly wheat that they were concerned about, was in deadly peril of not having enough to eat. And he predicted then, if we didn't solve this problem, there would be mass starvation by the 1930s. Okay, so what was going on? Well, the problem is basically that we didn't have enough fertilizer. So in the late 1800s, the big fertilizer was in the Peruvian islands. It was bird guano, so bird poop. So birds had for thousands of years pooped on these rocks, and we had taken this fertilizer, we had taken this guano and used it as, it was an incredible fertilizer. It still is. You can actually buy it on Amazon. Okay. Now, this was, but you can imagine though, this is a finite resource because, you know, there's only so fast these birds can go to the bathroom, right? So what we have to, so then we turn to the Chilean, in Chile, the nitrate reserves. And there are actually ghost towns in Chile from all of this extraction that we did of the nitrates out of Chile. And you can see there then the time frame of this, and actually you can also buy Chilean nitrate on Amazon as well. So here's the problem, and you know, we're not going to have enough fertilizer. And so Crookes' call to action was to the scientists that we need to find a way to make fertilizer, and it's through chemistry. It's the chemist who's going to come in and save the day. So let's see that. The key to fertilizer is nitrogen. Okay, there's also potassium in there and phosphorus, but the key here is nitrogen. And where are we going to get this nitrogen from that we need for fertilizer? Well, you could look to air. Air is mostly nitrogen. Okay, so in fact, air is about 80% nitrogen. Okay, so 78% nitrogen. The problem with the nitrogen in the air is that it exists as N2. So we have two nitrogen atoms that are bound together. And in this way, this nitrogen that's bound, this is a very stable molecule, and it's very hard for the plants then to use it. So what we need to do is break that bond, and we do something called fixing it. So we need to break this bond between those two nitrogens and fix it so it can be used as fertilizer. And that's exactly what Haber and Bosch did. So, and I think it's important to point out that Fritz Haber was a chemist, Carl Bosch was a chemical engineer. It was through this collaboration of scientists from different areas that you're able to attack a huge problem like this. And what they did then was find a process where they could take nitrogen and break the bond here and use that together with hydrogen to make ammonia. Okay, so what we're doing is we're taking one nitrogen atom and now we're binding that one nitrogen to three hydrogens here in ammonia. And this single discovery was the most important technological advance of the last century. Okay, how can we see that? We can see that in terms of the number of people and the population on the planet. This is a plot, the red line is showing you the world population supported without synthetic fertilizer. And this is the total world population. All of this, so half of our world is now supported. Half of the people on this planet are supported by synthetic nitrogen, or by synthetic fertilizers made through the Haber-Bosch process. Okay, so this type of chemistry is exactly the type of chemistry then that we're going to need to solve climate change. So let's look at that. This is just showing the Earth is warming, right? And it's kind of a scary picture of it because you're going to see it's going to get progressively more red. And all the predictions, as you've seen from the climate conferences, is that once we get to that 1.5 degree level, and we're approaching it very quickly now, right? A lot of things are going to be, we're not going to be able to turn back the clock. Okay, so what's causing this change? Well, okay, so let's first talk about what the greenhouse effect is. The greenhouse effect is basically, this is the atmosphere over the Earth, and the sun shines on the Earth with that, so that's a solar radiation, and we re-radiate the heat off, and a substantial portion of that heat escapes. Okay, what keeps it from escaping, from all of it from escaping, are these molecules that are in the atmosphere, these chemical molecules like CO2, methane, N2O. These are molecules that are floating around. The atmosphere is important. If we didn't have the atmosphere, we didn't have any of these molecules up in here, we'd all freeze, right? We need this in order to live at the temperature that we do. Now, the problem is that what we have done is we've put a bunch of extra molecules up here in the atmosphere. So we have more CO2 in the atmosphere, more methane in the atmosphere. We've put more of these molecules up there. They're absorbing the heat, and less of it's getting expelled into space. So that's why the planet's warming. So really, this is a chemistry problem then, right? What we're talking about are these small molecules, just like we saw in the Haber-Bosch process, small molecules that chemists then can work with. To give you an idea of the CO2 levels, you've all seen plots like this. Everything was fine for many, many years, right? This is years on the bottom here. And you can see that in about the 1800s, we start rapidly rising in our CO2. That exactly corresponds to fossil fuel emissions. Okay, so when we look, this line here, you can notice it looks exactly like the CO2 line going up. This is the total fossil fuel emissions, and that's a sum of, as you see here, green is what's been emitted from coal. This dark blue line here is petroleum. This is natural gas, and then there's cement. Cement emits a lot of CO2, cement production. Okay, so why do we have all this fossil fuel emissions? Well, all of this is coming from our energy use. So let's look at our history of energy use and energy consumption in the United States. So here back in the beginning of the country, we're using barely any energy. We have a lot less people then too, right? But what we're using is biomass. That's this yellow line. So that's like trees and burning, things like that. Then you notice that the change is in the middle of the 1800s, here's where coal comes in. And that's followed in the early 1900s by petroleum, and that rapidly goes up, and natural gas, right? You can see that here after World War II, we see nuclear come in, and that kind of levels out. There are a lot of political issues with nuclear, right? Hydroelectric, you can see we've kind of maxed out our hydroelectric, so we've dammed the things that can be dammed. But what you're seeing from this is you have to imagine, first of all, this is all the energy we're using on this side, and all of these are stacked on top of each other, right? So that's a tremendous amount of energy. The other thing you notice from this side is look how small renewables, this is like solar and wind, look how small that is of our energy picture. Now, you'll also note that this part right here where coal went down and natural gas went up, okay, exactly balanced each other. That's when we switched in this country from coal burning power plants to natural gas burning power plants. And that actually had a positive effect in terms of lowering CO2 emissions. And you can see that this is largest reductions and increases in CO2 emissions by country for the last decade. And you can see the United States actually reduced its CO2 emissions. Well, that's great, but you can see didn't balance out, right? Other countries are emitting more because they still need energy, right? So, so this is all where we've been in the past, but let's look going forward. And if we look going forward, you can see here, here's the 2020 line, and you see this dip in all the energy. That's when we all went home because of COVID, right? All our energy use went down. Okay, so what you're seeing here, that this is the part we just looked at where coal went down and natural gas went up. But this is now projecting out into the future over here. And you can notice that petroleum is still really up high here, as well as natural gas. Renewables only gets up to here even by 2050. Okay, so, but we're predicting the future here. What are these predictions based on? Well, they're based on, first of all, current laws and regulations. So at Penn, we're really pleased to have the Climate Center for Energy Policy that looks at issues like that. And it's exciting for me being at Penn that my research students as well get to get involved in working with the people in policy and learning about policy, because scientists really have to have an impact in policy concerning energy, right? And you're going to see that because you really have to look at the data and examine all of this. Okay, the other side is how do we take these lines down? So how do we get petroleum down and get the renewables line up? Well, the other part that this plot was based on was normal advances. So no big, whoa. Should I be worried about that? Okay. All right. So no big advances in science. So just kind of the normal incremental increases. All right. But we need really big advances if we want to, because what we want to do is make this line a lot steeper so we can get up and get closer to the top there. And we want to bring petroleum down. Okay. So as I said, this is the United States, though, and we want to look at what's going on in the world. And it's important to look at what's going on in the world because this plot here actually puts it very nicely. Shown on this side is the UN Human Development Index. And shown on this side, on this axis, is the energy demand per capita. And what you're seeing is that energy use is really intrinsically related to, can we get that thing at the top gone off the screen? Okay. So what we're seeing then is that energy use is really related there to the Human Development Index, right? That you're going to need more energy to get up higher here. And you can see here's the United States. We use a lot of energy in the United States. We'll come back to this Iceland over here. I just want you to note that Iceland has a little, but that's because they have a lot of geothermal energy, and we'll talk about that. But the size of each of these circles has to do with the population, how large the population is. And you can see that as you can see here, as India and China move up on this Human Development Index, they're going to need more energy. Okay, so it's important to look at the predictions for energy use for the whole world, not just the United States. So that's shown on the next slide here. And you can see here's our 2020 line, and here are the predictions out to 2050. So it's great. Renewables on this line at least passes coal and natural gas, but still out in 2050, petroleum is still the biggest one out there. Okay, so there's still issues on that front. The other thing that you should realize is that we don't, when we think about petroleum and energy use, a lot of us think about travel, transport. And I think it's important for you to realize that even if you don't drive or fly, you're actually using oil every day. So if this is a barrel of oil here, there we go. This is a barrel of oil here. Most of it here is used for transportation. Okay, so it's used for gas in your car, diesel fuel, jet fuel, all of those things. But an important fraction, that fraction up here, this 14%, that's actually where petrochemicals come from. And what are petrochemicals? Those are the chemicals that we use to make everything that you use every day. So whether it's your fabrics and fibers, your plastics, the body care products that you use this morning, you know, the shampoo in your shower, your detergents and cleaning supplies, all of your medicines and your medical supplies, these are all coming from petroleum. And what they're coming from is they're really a byproduct of the refining process for petroleum. Okay, so we get them at a low cost that enables us to use all these things because we're refining petroleum on such huge scale, and we're getting this as a byproduct and we're using it to make all these things. So as we want to think about using less petroleum, we also have to think about where we're going to get all these chemicals, not just where we're going to get all our fuels. Okay, so what do all these things have in common? What is it that we're trying to get out of either to make chemicals or fuels? And just as the fertilizer depended on nitrogen, all this stuff depends on carbon. That is, carbon is our key. So what I'm going to talk to you today about is that if we're not going to get it from crude oil, we want to think about the other places we can get it. One option is from methane. Okay. Another option is non-food biomass. So we don't want to use up our food supply, but there's a lot of carbon in biomass. This would be a great option, and we're going to talk about this in terms of setting up an anthropogenic carbon cycle. What if we could get the CO2 itself and use that? And then one last one that's been very big in the news is trying to use plastics as a carbon source. So we have a lot of waste plastics. All that plastic contains carbon. Okay, so let's start by talking about natural gas. Okay, so natural gas is primarily methane. Okay, so the largest fraction is methane. There are some higher carbon levels, carbon molecules. So methane has a carbon with 4 hydrogens attached to it. It's a very simple molecule. These higher chemicals here just have more carbons in them. Okay, so, and it's not just methane from fracking. So we don't just think of natural gas as we get it from fracking. Methane's actually around in a lot of places. So here's the natural gas and petroleum system. So that would be like fracking gas. But you also get methane from landfills, from enteric fermentation. And methane, it turns out, is a more powerful greenhouse gas than CO2. Okay, it has greater warming potential. Is something not? Okay, sorry. Sorry for those of you online. We're trying to solve the problem. Okay, so, all right. So let me show you this beautiful picture of the United States, right? This is a satellite picture taken at night. And what you're seeing is light pollution, okay, all over the United States. And you're seeing big cities giving bright lights, right? So here's the Eastern Seaboard, here's Chicago. Maybe I'll make it a little easier by laying a state map on top of it, right? So you're seeing where there's big cities, there's bright lights. But then you also see a bright light up here in North Dakota. And there is no city of that size of those other cities in North Dakota. What you're seeing there is actually flaring gas. Okay, what do I mean by flaring gas? It's literally taking gas as shown here. So if we say natural gas is mostly methane and burning it. So that's reacting it with oxygen to make CO2 and water. That's what that bright light is. All of is natural gas burning. And why do we do this? We do this because it's very expensive to transport natural gas because it's a gas. Okay, so running pipelines is very expensive. It's also hazardous. You can liquefy it, but that costs a lot of money. Very energy intensive as well. So, and it's important to realize then that this flaring of natural gas is not just happening in North Dakota. This is now no longer a picture of light pollution, but this is actually flaring gas all over the world. Okay, so you can see here, in 2019, we flared 150 billion cubic meters of gas. Okay, so the question is, you know, yes, it's a good thing that we're taking the natural gas, the methane, and converting it to CO2 before we release it, because if we released it as methane, it's a worse, as I said, it has greater global warming potential. That means that the molecule of methane is going to absorb more heat than one molecule of CO2. Okay, so what could we do? Well, we could convert it to then, if we could convert it to a liquid, we could then move it. So one technology to think about is taking methane, a gas, and converting it to methanol, which is a liquid. So remember, methane had these 4 CH bonds here. And now what I've done is inserted an oxygen into one of them. And that then makes it a liquid, right? Because we have hydrogen bonding. Okay, now to run this process, we do this on large scale. And we do this by taking methane and we steam reform it look at the temperature here, 700 to 1,000 degrees Celsius. So you can imagine this takes a lot of energy to make CO and hydrogen, and then we recombine CO and hydrogen to get methanol here. So this requires an awful lot of energy. It also requires a plant like the one shown here. This costs $1 billion to build. You have to do this chemistry on large scale in order to make it profitable. Okay, so we can't put one of these $1 billion plants in every one of those locations. Now, when you look at this, what I suggest you do so if you're not a chemist, think of these as tinker toys, okay? If you wanted to get from methane here to methanol here, I doubt that you would break every one of these bonds. You wouldn't take off all of those hydrogens and then put them back together again in the next step, right? It's very inefficient. And yet that's how this process works, right? So you spend all of this energy tearing your molecule apart and then you have to put it back together again. So instead, what we'd like to be able to do is as shown here, take our methane plus an oxygen molecule, then just break this bond in oxygen, similar to the way they did in the Haber-Bosch process of nitrogen, and then put that oxygen right here in between one of the hydrogens and one of the carbons. Now, if we could develop a low energy process to do a reaction like this, then we could think about, even having, portable methanol plants where we could drive up to landfills or to those sites where we're flaring gas and convert it into methanol and then move it. So in order to do something like this, what we have to do and to get a low energy process is to create a catalyst. Okay, and that's exactly what the Haber-Bosch process did. So Fritz Haber created a catalyst that would do that reaction. So what is a catalyst? The idea here is if you go from your reactants on this side to your products, you would go by this pathway where you have to go up in energy and then over a barrier down to your products. Where if I have a catalyst, I can go by a different path that requires less energy. And the catalyst doesn't get used up in the reaction. So let me explain that a little differently, and I credit Joshua Kritzer at Tufts for this. Think about it in terms of your energy levels. You're starting out and you're hungry, you're hangry, right? And you want to be fed. But in order to do that, you'd have to cook your food, right? So that's going to require some energy. You're going to have to get over this barrier to get that happy, fed, low energy feeling, right? Now, what if there was another way? What if you could order food, right? So you have a different path here, right? But it's a path. I had to decide what restaurant do I want to order from, what do I order, and then I have to pay the delivery person. But I use less energy on this pathway, right? That's what a catalyst does. So imagine your catalyst here is actually your phone, because at the end of this, you still have your phone, right? Your phone helped you to do this process. So that's exactly what we're thinking about in terms of the catalyst. So if this is our reactant to products, and let's say our reactants over here are A, B, and R, and we're going to react these two together to put R between A, B, and make ARB. That's our fake molecule here. So that's our reaction shown here. Our M here is going to be our catalyst. And so what you're going to note is the M, our cell phone or our catalyst, first breaks the bond between A and B, and we form this species, right? Or now we have a bond between the metal in A and the metal in the B. And then R comes in, and the metal assists R and A in making a bond there, and then finally eliminates the product and regenerates the metal again. Okay, so that's what our catalyst looks like. And it doesn't get used up in the reaction. Okay, so in our group, what we're looking at are catalysts to take methane to methanol by such a cycle. So shown here, Hannah Zeitler was working on this project. She just graduated. Drew Newman is in the group now working on it. And really what we have then is we have a metal catalyst that takes a molecule of methane and breaks one CH bond. So I put the methyl group on the metal center. And then I have oxygen come in here. And then I have the last step of eliminating it off the metal center. So through this process, the metal is always there, right? It doesn't get used up in the reaction, but I start out with methane and O2 and I end up with my methanol product. Okay, so this is actually a system that Hannah was working on. And Drew still is that taking methane and activating the CH bond as shown here, inserting oxygen and releasing the product. Okay, so that's kind of what that type of a cycle would look like. And we're still working on this. This doesn't quite work this way yet. Okay, so that's a little bit about methane. Let's talk now about CO2. Okay, now the first thing we have to think about in CO2 is we hear about CO2 levels rising, right? And we think, well, there's all this CO2 in the atmosphere. I can just use CO2 for my reactions. But let's think more carefully about that. This was our picture of air. Remember, air is mostly nitrogen. CO2, even at 400 parts per million, that is still 0.04%. So there are very few CO2 molecules roaming around that I can capture. And that's actually led to an entire field of what's called direct carbon capture, direct air capture of CO2, where you build these big systems like this with fans. This is the world's largest direct air capture CO2 storage plant that opened in Iceland. And sadly, you see that you're only capturing the equivalent of 870 cars annually, right? Yet there's a lot of technology that goes into this, and we're going to see more and more of these plants. At Penn, we were actually very lucky to hire in 2020 Jennifer Wilcox, who's one of the world's leading experts in carbon capture. And then we hired her in fall of 2020, and then in 2021, the Biden administration stole her for the Department of Energy. So that's good for the whole country, not so great for Penn. But we're going to be seeing more of these types of carbon capture plants. And typically, if you locate them, let's say near a power plant where you have a lot of CO2 in the atmosphere, that's going to be more efficient. Okay, so this is the goal here, is to take CO2 and create an anthropogenic carbon cycle. That means, for example, we could take CO2 and do hydrogenation to make methanol here. And we know how to take methanol on to make petrochemicals and fuels, so we could do that. And then we could still burn those things if we were able to capture the CO2 and go around. So the idea here is to be like if we were like a human plant, right? That we could take the CO2 and convert it back into something we could use and keep going around the cycle. That way we're not letting any more CO2 out. Okay. Now, there is actually a plant in Iceland that takes CO2 plus hydrogen to methanol. This is the George Olah Renewable Methanol Plant. It's only located in Iceland because Iceland has all of that geothermal energy that I mentioned. So it costs a lot then energy to run this plant. We'll say that. So this, at the current time, this is the only place you can site a plant like that. This is the reaction they're looking at, CO2 plus hydrogen to methanol and water. This operates at about 200 degrees. They use a catalyst as shown here. And these are the enthalpy and entropy, which won't mean anything except to the chemistry majors here, right? And those chemistry majors will also be able to calculate that based on these delta H and delta S, you then will get your KEQ will increase as you lower the temperature, right? So for the rest of the people in the room, basically what this means is I'm going to get more product at lower temperature. So again, we need to create catalysts that can work at lower temperatures, right? So that's the goal. We need new catalysts that will promote this reaction at lower temperatures. Now, before I leave this methanol plant, I do want to point out that, as I said, the reason that it can be sited here in Iceland is because they have all this geothermal energy. And so shown here is the geothermal energy plant. Well, I can't get this pointer to work anymore. I don't know where it is. Okay, the geothermal energy plant, which is located right next to the Georgia Law renewable methanol plant. But what you'll notice is this Blue Lagoon Spa. Now, the Blue Lagoon Spa is a very ritzy spa. It's maybe some of you have been there. It's a beautiful location, but this blocks this, you can't see my pointer. This ridge kind of blocks the people in the spa from seeing that they're actually bathing in the water from the geothermal power plant. So this is not natural hot springs, okay? Nevertheless, it's supposed to be a wonderful place, and I do hope to visit, and I will bathe in the water. It is safe. Okay, so how do we create a lower energy process? Well, we can take a clue from nature. Okay, nature's approach, which does this, under room temperature conditions, right? So low temperature is we can take CO2. This really isn't.
It really isn't. And I didn't bring it back. I'm sorry. It probably just needs more batteries.
Oh, all right. I will use my pointer on the screen.
Yeah.
Okay. Okay. So sorry, I advanced. Okay. So so this is nature's approach, where you take CO2 and you take protons, and you can get your electrons here from this molecule, and you can fix the CO2. And the way that nature does this is by doing it. Don't worry, you don't have to understand all this. I can't understand all this. I know a lot of the students, the biochem students, could probably understand all this. But the key to this is that each of these numbers is a different enzyme. So enzymes are nature's catalysts. And what nature does in this process is it takes one molecule, makes a different molecule, and then passes it off to the next catalyst. So for example, you have CO2, and then it's converted here to formic acid, and then that's passed off to another catalyst, which converts it down the way. And this is called cascade catalysis. So instead of having one catalyst, which does the whole reaction, they pass it off. Okay, maybe if you called, no, I don't know how to make a cell phone analogy there. Okay. All right, so Melanie Sanford at Michigan did some beautiful work where she used this tandem or cascade strategy to convert CO2 to methanol. What she did was to use 3 known catalysts. So the catalyst A, catalyst B, and catalyst C were all known to catalyze these individual reactions of first doing a hydrogenation of CO2 to formic acid, and then taking formic acid onto the ester, and then hydrogenating the ester. And so she put 3 catalysts that were all in the literature together to do this. And when she did that reaction, she got a turnover number of 21. Now, what's a turnover number? A turnover number is how many times your catalyst will go around a cycle before it dies. Okay, so if you think about this in terms of your cell phone, you could order dinner 21 times, and then you would need a new cell phone. So not a very efficient, this isn't gonna obviously work on large scale. But then what Melanie did was figure out that it turns out the reason is that this catalyst C was acid sensitive, and this scandium triflate was generating acid. So what happens here is catalyst B and catalyst C were incompatible. Well, in our lab, we actually had a catalyst that did ester hydrogenation. And not only that, we got higher turnover numbers, so more calls on our cell phone, when we had scandium triflate present. So what we're saying is that we have a new catalyst C that works well with catalyst B. Okay, so let's throw this into Melanie's system. And we did that. And we found, together with Melanie, and this is really important in science, is scientists working together, because you can't do everything on these huge problems yourself. So then we find out there's no turnover. So what's the problem here? Well, we investigated again, And what we found out in this case is that one of the phosphine groups from this catalyst was ending up on our catalyst C, and that was killing catalyst C. So basically, catalyst A is incompatible with our new catalyst C. Okay, well, what could we do about this? Well, you can see that this ruthenium center is it's shedding this PME3 group. So what we decided to do was tie those groups all together. So create bonds between those so that it couldn't just lose a PME3 group. And that's what we did as shown here. So we have these phosphines tied back. So this is all attached, so we can't just lose one of the phosphines. And when we put this together, what we found out was we got a turnover number of less than 10. So we did all this work and we're not as good as what Melanie had to start with. So what's the problem here? Well, the problem here we figured out was catalyst C was too slow. And so we were able to change catalyst C to a new catalyst, and now we can get 400 turnovers. So definitely improvement on the 20. This was exciting work in our lab, and even more recent development is this work from the Byers lab in Boston, where what they did was they put the catalysts in molecular cages, and they kept all the catalysts separate from each other. But the molecules that the catalyst was giving off, these small molecules, could go from one catalyst to the next. But the catalysts themselves were protected from each other. And under these conditions, now he can order 100,000 dinners, right? Okay, well, this is great, but it turns out that hydrogen is currently sourced from methane. And the way that it's sourced from methane is that terrible reaction I showed you at the beginning when we were talking about methane, where you have to heat this thing at almost 1,000 degrees Celsius, right? So this costs a lot of energy to make hydrogen. And you're also producing CO, which isn't great either. So instead, what we'd like to do is get our hydrogen from water. And so there are a lot of scientists working on this problem of taking water and developing catalysts that will use sunlight here, so renewable energy, to make hydrogen and oxygen. And then you could use that hydrogen in processes like I just showed. But an even better idea might be maybe we don't need to make hydrogen at all, because hydrogen is really protons and electrons. And that's the way nature does it. So remember, nature takes protons and then it gets its electrons from here, and it never actually goes through hydrogen. And that is where the DOE has made a huge investment in setting up 2 very large hubs in the United States to look at artificial photosynthesis. And one of those, so the idea is basically to take CO2, hydrogen, ammonia, sunlight, and get out liquid fuel. Okay, so CHASE is the Center for Hybrid Approaches in Solar Energy to Liquid Fuel. And its mission here, so that you get CHASE by an acronym here, its mission here is to take the small molecules found in air as chemical feedstocks and sunlight as the sole energy source. So what we're going to do is take sunlight, irradiate here a semiconductor surface, have catalysts that are attached to that surface, and then we're going to run this kind of cascade system I just showed you in terms of getting one compound to go to another and all the way down to liquid fuels. Okay, now you can imagine this is a huge thing here. This is going to take a lot of people to put this together. And that's exactly what CHASE, this is exactly what CHASE looks like. So CHASE has scientists from 6 different institutions here, all working on this problem. It has chemical engineers, it has chemists, it has people who work on semiconductors, it has catalysis people like my group, it has spectroscopists, computational people, all working together to try to figure out how we're going to develop this system and make it work, right? Because we need really good catalysts that are going to be able to attach to those surfaces. We need things to absorb the sunlight, to convert it to electrons, all working together on this problem. And this is then, you're going to see more of these huge investments, and this is what we're going to need as we move forward to attack a huge problem like climate change. Okay, so I'm running a little short on time. I'm not going to talk about biomass, but I do want to mention plastics because this is not one that people think about a lot. Yeah, probably some of the students won't get this joke. But yeah, one word, plastics. There's a great future in plastics. And there really is. I mean, plastics has so many benefits, right? In terms of food storage, we can keep food for so much longer than we could before. In lighter materials for transport, in personal protective equipment, insulation, medical supplies, all depend on plastics. But right, the problem with all of this is where plastics are ending up, right? Like we can have plastic bags in the ocean, we can have these huge piles of plastics that are, basically islands in the oceans, right? And we think we're doing our job by putting it in our recycling bins, but the actual amount of plastic recycled is surprisingly small. So this is the amount here, green, that's recycled of plastic, okay? This is the amount discarded. This is incinerated here. And sadly, as we move forward, you can see this is the difference between what's recycled and what's discarded. And you can see it's just getting, and what's generated, and you can see that's just getting bigger in the future. Okay, so what's the problem? That recycling is really not profitable. And so you can see here, this is recycling rates in the United States. You can see then, these are the different labels, the recycle codes you'll see on your plastics, right? All the different uses, but you can see these recycling rates are really small. I mean, if you look at polypropylene, for example, that's 1%. Okay, but when we look at what these polymers are, these plastics, you can see that they're just carbon and hydrogen, right? That's essentially what we need to make fuels and chemicals. So when you look at a plastic bottle, these are just different kinds of polyethylene. So it's whether they're linear like this and they pack very tightly and make these hard surfaces, or we can have these more flexible things if we have these branch ones. But these are sources of carbon that, again, we can use to make our chemicals and fuels. So what I hope, but in order to do that, what do you need to do? You need to develop catalysts to do that, right? So that's something we're working on as well. So I hope I've shown you today is that we really need to move away from getting our chemicals and fuels from petroleum, but we have to keep in mind that it's also our chemicals as well as our fuels. And we need to think about all of these other ways of getting there, right? These other sources of carbon. And in the end, we're back to this plot, which basically says we need new regulations and policy. And that's why it's so important that scientists go out and argue for the policies that we need, things like a carbon tax, right? And on the other side, we need big advances and investment in science. So big investments like the DOE is making in artificial photosynthesis. And so with that, I just want to thank a lot of funding sources, NSF, DOE, the Vagelos Institute. This is a COVID right after we're still separated outside. And I want to point out Sophie Rubashkin, Barnard College, 2015. Former graduate student, now on a postdoc at Pacific Northwest National Labs, actually working on CO2. So with that, thank you.
So doesn't that make you want to keep studying chemistry? Yeah. You guys picked a good grade here. So we'll take questions. We'll be able to field them, both people who chat questions here into the to your little chat feature on if you're watching remotely, or it'd be great to start with some questions from the floor from my middle row here of students. I could, but I don't want to put that much pressure on you, but Want to start the conversation, anyone?
I'm a CS major.
Okay, well, that counts. Do you want, I mean, this was definitely a conversation to make many majors think that there was something to think about here.
I didn't know that sort of there was a system where this is essentially solving two problems at once. Like it's solving the plastic problem that we have and also trying to get new energy, and really whoever can solve this energy problem, that's the next Google. That's going to create, I don't know, like 100 times the amount that, you know, of revenue, net worth of company that Google was. And so this is the next big thing, right? I'm just here for context.
Good. Good. Oh, I'm actually not, I can't, there's going to be feedback,
Okay,
so I
yeah,
have to
so I'll
step
just-
away.
Just for the people who can't hear that, just a student commenting that how interesting it is to recognize that here's scientists trying to solve two problems. We have an energy problem and a plastics problem. And, you know, if you hadn't thought about it before, understanding that there could be a linkage there is kind of exciting and, you know, quite lucrative. And it is part of why I think as chemists, we really think about the continued importance of the material world. So you're a computer scientist. My bosses might say, well, Rachel, why don't we just do why don't we do chemistry just on the computer now? That would save us a lot of money because we would not have to renovate Altschul. But the reality is, you know, we live in this material world. And I think that's something that as a chemist, we think about a lot. The things that we eat and drink and keep us healthy and drive us, you know, these are things that actually do require materials. We can't just artificially intelligent them, you know, and still. So yeah, it's an interesting linkage. And I think the way that Professor Goldberg, like the way she frames it in terms of molecules, it's kind of obvious to us that there would be connections because plastics are just those C's and H's. And hopefully that came through to everyone today. Yes, hang on.
This makes me wish I was a chemistry major. So.
Well, we have some major declaration.
An OCHEP intro class. I thought the juxtaposition or how you started to frame it in terms of the COVID vaccine was really interesting and the big leaps we took in 9 months or 12 months. A lot of that happened in private, so like Pfizer, right? And so I guess I was wondering if you could speak to how this sort of work interacts with private companies and where we think the center of advances are going to be.
So quickly, I'll just repeat that. So the question is
I don't know that this.
this not on? Would you want to just
Yeah.
repeat it with your mic then? Easier.
Oh, maybe I should just turn this off. Okay,
Oh, this is going to be best. Okay.
okay. So the question was about the COVID-19 vaccine was fueled a lot by private companies and what kind of role private companies can play in as we move towards finding solutions to climate change. And I think that's an excellent question. And in fact, all of these energy companies are pivoting already, and we can help them to pivot faster. So they are all prepared. They have carbon tax plans all ready to go. And we just need to pass kind of policies to make all of those things more appealing for them to go along those lines. So they are absolutely looking at all of these things. But there's a lot of fundamental science that has to come into play first. And what I love about the book, The Alchemy of Air, is that it really shows how the fundamental science advances that Fritz Haber made in more of an academic setting, then we would not be where we are without Bosch doing all the chemical engineering at BASF, right? At a company to take that to a scale. So you actually are going to need everybody working together on this. And there's going to be multiple solutions, right? We're not going to be able to be completely dependent on one energy source. I mean, maybe in a really long time we can get completely to solar, but not on the time scale that we need.
You want to look at that?
Oh, okay.
So there's one about carbon sequestration. Is it worth it? Would it take more energy to break down plastics? How would you use methanol? Any of those that you want to tackle?
So someone is asking if it would take more energy to break down plastics into small molecules and use them to synthesize new plastics than to recycle them. So you are correct that that would take more energy. That is correct, that you are then you're taking a lot of energy to break those bonds, because it is actually the reason it's so easy to make plastics is because you release so much energy when you take a small molecule like ethylene to polyethylene. Okay, but we're not proposing that you go back to ethylene. We're proposing that you are using those to make other molecules. And so it will take some energy to do it, but you're giving a second life to that carbon, at least a second life. There are also some people that are trying to upcycle those polymers into more specialty polymers, which means you won't have to take as much virgin ethylene on to make some of these exquisite polymers. So there's, as I said, there's going to be a lot of solutions that we're going to need to develop all of this. And it's not a one, the Google is a good example. It's not going to be one Google, there's going to be Google and all the other companies that have come up as well, right? Yeah.
I do have a question about so after, let's say we found a solution, you'd have to sort of do this at scale. Do you envision big oil and a lot of the sort of current really big players in oil being able to pivot? Or do you see a lot of more like newer, smaller companies coming in, taking this technology and rebuilding it to scale?
That's a great question. So the question was on scale, whether these new technologies would be immediately taken on by a large oil and gas company, a large energy company, or whether you would have small startups that come into play. And right now there are small startups that are coming into play that are doing things like carbon capture and all of these. And then I don't know what the model is because we're still developing it, whether those would then be absorbed by these larger companies. Larger companies do have, though, good investments in clean energy because they know they have to. They're publicly traded companies, and the people who own the stocks are saying we need this to be clean. So
Including colleges and universities.
exactly. But you can't just, you looked at those plots and saw how dependent we are on petroleum today. It's not like you can just turn off the pipeline. I think that's the important thing to realize, is that you can't just say, don't use oil anymore, because that's what we're using mostly, right? So we could turn off all the lights, start there, but
Who built the oil methanol plant?
who built it?
Yeah, who put the money into it?
I don't know. Iceland? I don't actually know that.
Are there other questions?
Oh, are there more questions?
Just how could you use methanol, or what do you think about carbon sequestration? Is that really worth it?
Okay. How could you use it? Oh, how could you use methanol once it's created from natural gas? Methanol can actually be used as a fuel itself. It can also be, there are actually also technologies that we already practice where we can take methanol and upgrade it to lots of things, to ethylene and to all sorts of chemicals. It's kind of a platform chemical. So we can actually take, there's a process to take methanol to gasoline, actually. So the technology for transforming methanol and using that is already on the books. People are already practicing it. And the other question was, is carbon sequestration worth it? Boy, we have to figure out something, because all the predictions and all the plots show us that we really have to not just get to zero, but we're going to have to absorb some of that CO2. So yeah, we have to figure out a way to do it. Currently, we're not quite there, but as you saw, it's a small amount in the air. So capturing it is really expensive. But we do have to find a solution, so yes.
Are there other questions? Okay, well, I think we've satisfied our people watching remotely. Thank you guys for joining in. Thank you for being in the room. Let's join me again in thanking Professor Goldberg.